Influence of electrical currents within the cellular membrane on movement. I chose to do my topic on electrical currents within the cellular membrane and how these electrical currents are important within the human body in terms of movement. Electrical field within the membrane. The inside side saw is composed of negative, whereas the outer membrane is composed of positive, which results in an electrical field within the membrane. Anything positive will flow in the direction of the field, and negative will go the opposite direction. The equation depicted here is the one that we used in class in order to get a value for electrical fields. And the picture that is depicted here is one of many drawings that could be used to represent an electrical field between ions of opposite charges. And so basically, what happens is the membrane has one side that is positive, one side that is negative, and because of this, the inner membrane is composed of electrical field that acts in the same way as the electrical field that is discussed in class. So if something negative is placed in the electrical field, then it would flow in the opposite direction of the electrical field, and if something positive is placed within the electrical field, it would act in the same direction as the electrical field. Membrane resting potential. The resting potential of the membrane is negative 90 MV. The potential is increased dramatically when an Na channel allows a lot of Nas to come inside, leading to depolarization resulting in action potential. So basically, the picture all the way to the right shows how this process works. So ATP molecule attaches to the Na transporter, allowing and causes a conformational change and allows Nas to be pumped out, while two potassiums is attached, and the conformational change is changed back, and the 2 potassium is pumped to the inside of the cell, and then the ATP is then hydrolyzed back into ADP, and this process is repeated over and over again. Where depolarization comes into play is when an Na channel that is present on the cell membrane opens and allows an influx of Nas, a lot of Nas, that causes the resting potential of the membrane to change from negative basically to positive. And once the change is so great, and action potential is fired down the membrane. Electrical current. When depolarization occurs, it causes a voltage uprise. This voltage is then used to open the voltage gated Na ion channel, which allows even more Na to come in and keep the action potential going. The picture right here depicts a voltage gated ion channel, and this voltage gated ion channel only opens when it is hit with voltage, which is coming from the action potential that has been created. Once the voltage gated ion channel is open, it allows a lot of ions to come in and within the inside the membrane, which is important because the action potential that is created, you want to keep going down through the whole membrane in order to reach the axon helix, reach the end of the axon helix in order for the neurons to be transmitted. It can't do this unless the voltage gated ion channel keeps ions coming in each time the action potential reaches it, in order to keep the energy high for the action potential, so the energy from the voltage won't go away. And this equation here, as said earlier, is the same equation that we used in class in order to depict how to calculate voltage within a system. Neurotransmitter. Once the action potential reaches the end of the axon helix, the vesicle containing the neurotransmitter is transmitted either to another axon helix or to the muscle, which then contracts, which allows movement. So basically, when this action potential reaches the end of the axon, it is then neurotransmitters are stored in vesicles, and these vesicles are created by calcium. Once these vesicles contain the neurotransmitter reaches the end of the axon, it has 2 choices. It either, as depicted in this picture, can be transmitted to the dendrites on another axon helix, and the process can be repeated, or it can be transmitted to our muscles. And once it's transmitted to our muscles, it causes a muscle contraction, which is very important for us in order to be able to move. Just as a little side fact, I want to mention the myelin sheath, which can be placed on the axon helix, and once a myelin sheath is placed on the axon helix, it causes basically the electrical current to increase, and this is important because it causes action potential to occur quicker by allowing more ions to come in at a quicker rate through nodes on the axon, and only can come in at specific sites, which is very important to how the action potential can quickly reach the end of the axon. And this is my source that I use. I think I kind of got lucky because it just so happened that the topic that we talked about in class and the topic that I talked about in molecular cell were the same, because I just got finished talking about molecular cell bio, talking about in molecular cell bio about this topic just when we before we started talking about it in physics. So only thing that I really need was my molecular cell biology book in order to help me understand the topic, which I already pretty much understood. So this is the only resource that I had. This is the end of my presentation, and thank you for listening.